here. And then once you send the form, then you go and see them and talk to them. Okay. First,
okay.
you send the file back. Complete.
So we need to go on now because we have a long afternoon with a mixture of presentations of tentative scenarios to reach a sustainable energy in 2050, and after that, critics by scientists on some drawbacks of this so-called sustainable energy. So first of all, we welcome Yvonne Deng. She used to be a physicist, but now she is a consultant with Ecofis, and she will present us this reflection on the transition to sustainable energy. Please.
I moved this, so we'll see whether it works.
Yeah, it's good.
Can you hear me?
Yes.
Good, then I don't have to project my voice. Well, thanks for making it to the afternoon session, those of you who are here. And thanks to the organizers for giving me the opportunity to present our scenario. I realize that by now you probably all have scenario overload, so I will try to speed through the bits that are the same in all these presentations. And I'll try to point out the bits that might be a little bit different. This particular scenario was basically an energy scenario that Ecofis came up with, and then WWF picked it up, and we partnered on launching it to the wider public. So that's why WWF is on this slide as well. And I'll tell you a bit more about that later. And I will stand on this side. Just a few words about Ecofis for those of you who haven't heard about us. We're an energy and climate strategy consultancy. We've been around for about 27 years. We were spun out of Utrecht University in the 80s by a bunch of physicists. And we've been advising governments, non-governmental organizations, and corporations on energy and climate strategy ever since. And our mission is a sustainable energy supply or a sustainable energy system for everyone. We have a bunch of offices around the world. We work internationally, but we're headquartered still in the Netherlands. Just a quick overview of the kind of clients that we work for. You see WWF there, who partnered on this project. We've also had input into the Greenpeace scenarios at the beginning, into their demand side scenarios, and a lot of my work involves actually working with the Shell scenarios team. We provide them with the renewable energy estimates that they use for their world energy model. Really quickly, I have 3 slides that I always show as an introduction. Nothing new for you, so I'll skip through them fast. Why do we think we might need a sustainable energy system? Why can't we carry on as we are? We have an increased demand of energy driven by both population growth and wealth. What I'm showing here are the assumptions on GDP and population, which we've used as exogenous inputs into the Ecofis energy scenario, just so you can cross-check them against the things that you work with. I also have to say that this scenario, as you saw on the front slide, is already 3 years old, and the base year was 2005, so it's a little bit out of date, but we think that the learnings from it still hold, even if the timescales will have shifted slightly. So we have an increased demand for energy services, at least, and that at the moment still means an increased demand for energy. We're currently relying on a bunch of energy sources which are finite. They might not run out tomorrow or the day after tomorrow, but they are all finite. And so at some point we'll see price increases, and the first one to be hit will be oil. And then for those of you who think that's an important driver, there is climate change to consider and the need to reduce emissions in the medium to long term. And currently, as you all know, we're on the route to not doing that at all. And the longer we wait, the faster we'd have to abate later on. Otherwise, and that gets harder and harder as we go on. So I'll skip quite quickly through that, but I think that's we all agree on the need for the sort of making our energy system more sustainable. So what happened about 5 years ago or so, Ecofis, which has been active in lots of different areas of energy and climate, we've got a lot of industrial experts, building experts, a lot of renewable energy experts. We got together and we said, can we just put this all into one scenario and actually take the Ecofis approach to each of the sectors and see how far we can drive this? It's very much supposed to be our view on the system. And the research question we asked was, at the time, is a fully sustainable global energy system really possible, just technically? We're physicists, so we said, let's just put aside the political, social constraints, etc., and let's just see if we could throw out all this technology that we have there. Would it be possible by the middle of the century or so? And I need to define my terms here just to be clear. What I mean global in the sense that we're looking at all of the regions in the world, so there's no trade in and out, and in a way that makes it simpler. We mean energy, so that means heat, fuel, and transport. So we're not just looking at the electricity system. And we wanted to find out whether a sustainable system was possible. And with sustainable, we mean at least renewable. And for some of the sources, of course, that means a lot more, especially biomass. So we also have additional sustainability parameters on there. And by definition, anything that's reliant on a finite fuel is not sustainable in our view. Now, we think it can be done, technically only, and this is how. Now, I'm a consultant, I like to lead with the answer, so if you want to fall asleep after this slide, that's okay, you'll know everything I have to say, but I'll go into a lot more detail after. I'll show you a bunch of graphs like this, and apologies for the simplification. I know you're all physicists, you know, but I'll say it anyway. You'll always see an x-axis, which is time, running from 2000 to 2050, and our base year was 2005. And you'll see on the vertical scale always final energy. We've also converted this into primary energy, but we tend to work in final energy because we're traditionally coming from the demand side. So that's how we express the values, and also because renewables, depending on how you represent them, get a bad rap on the primary energy graphs. So we like to show them in final energy. And the overall outcome, and I know you'll all find this very controversial, but we can debate, is this. In the dotted line, you see a rough approximation of what we thought a baseline might do. This is not necessarily calibrated to IEA, etc. And in the areas, you see what we think a sustainable renewable energy system could look like. So as you can see, there's a lot of demand-side efficiency there to reduce overall demand. That's not easy, but we think it's possible. Then you supply your energy with ideally renewable sources, both power and heat and fuels. And then we do think there's just a small amount of fossil energy, which is really quite difficult to get rid of. So we have a little bit of fossil actually primarily left in 2050. That's primarily in the cement and steel sectors. This is the overall picture. This is the summary of it all. And now I'll go into a lot of detail. I was told to focus on methodology, so it's a bit of detailed methodology. Usually I don't do that, but you're the sort of audience that I think might appreciate it. It's really a very simple model. It's what you might call a normative approach and what you might call just an accounting model. There's no complicated optimization. We're not doing differential equations. It's literally just going through, counting up stuff, and seeing how it can change over time. Okay? And we do make sure that supply and demand balances. I don't know how you cannot do that. And the way we do that is we start on the demand side. Energy demand is just the product of the sort of activity, the energy services activity, and the intensity of that activity. We see how we can push both of those levers over time, and then we multiply them up. That's really all there is to it. And we do it for electricity, fuel, and heat. We split our demand into 3 demand sectors: buildings, by which we mean both residential and sort of commercial, tertiary, transport, including all of the transport, aviation and shipping, and industry. There's also other, agriculture, fishing, etc., and we just scale those with these main 3 because that's really they're kind of a mixture of the 3. And then once we've got our demand, our energy demand, we then go to the supply side. We first estimate the potential for the various sustainable options. It's a separate exercise, exogenous, that goes in, and then we literally just match them up following a merit order that we predefine, which is sustainability driven. And we just go, right, first we're going to use this source because we like it, up to the potential within the region, etc. See how far we get. Then we go to the next source, etc. So we first use renewables other than biomass, because there's lots of them and there are fewer concerns. Then we use biomass, and then we use the conventional sources. I'm going to go into even more detail on this slide, in case that was too fast. So basically, I'm going to show you exactly how the model's built up. Energy flows from the left to the right, but actually the calculation goes from the right to the left. So we first define all of our various demands. That's for all of the various carriers in the 3 sectors. We then add them all up actually that's a simplification step, so we just say, okay, we need so much low temperature heat in a certain range and so much high temperature heat, we need so much electricity, etc., but we're not going to trace exactly where it comes from and where it goes. So, then we do this separate step where we estimate all of the potentials, first off, without saying how we're going to use them. And then we do the matching where we say, okay, let's use the renewables first, then the biomass, renewables, and then the fossils, and we do that separately for each of the carriers. Okay? And just to say, there's a sort of quite a detailed study that we did on biomass potentials, because it's something that you really want to think about. I'm not going to go into much detail there, but if you have questions, do ask me after. We spent quite some time trying to get the potential for that right. Okay. So then I'll start showing you results. Demand side first. Just quickly, again, I don't usually show this slide, but just to show you that, because on the following slides I'll say that we can do a lot of this with efficiency. So we're not making any assumptions or any dramatic assumptions on reduction in energy services. We think it's really difficult to communicate scenarios anyway that make reductions in, say, lifestyle comforts, etc. So we focused on efficiency. And we have some modifications to activity, but some of those are extrapolations of what's going on anyway. And so on the left there, you can see the drivers of population and GDP, which we took from other sources. We didn't change ourselves. And then this is what we came up with, sometimes based on other sources and sometimes on continuations of trends or slight modifications on those, which are per capita activity indicators. So for buildings, that's square meters. For industry, it's production, primarily in the heavy sectors. And for transport, it's person or ton kilometers. Okay, and that's the overall picture. So this is the overall demand in the 3 different sectors. And as I said, we have about a doubling of overall activity there, so most of this is done with efficiency. And I want to spend the next couple of slides talking you through the efficiency assumptions, just so you can see where they come from and check them against your own assumptions. Starting with industry. Obviously, this is quite simplified. We looked at 7 different industry sectors, and 4 of them we treated in some detail. Those are the heavy industries, which are a bit more homogeneous. Then there are sort of 3 sectors which are quite heterogeneous, where we just made generic efficiency assumptions. But basically, we think that if you assume some material efficiency, and you then assume a really fast and directed rollout of the most efficient technologies already available by today, and then a slight gradual improvement of those best available technologies by 2050, as well as shifting to recycling or alternative pathways such as in cement production, you can at least stabilize demand in the industry sectors. So just again to show you, this is our activity indicator, this is our efficiency indicator, and the 2 of them combine to make that picture. So just to be clear that most of the change happens on the efficiency side. In buildings, as we've heard already, you have to think about the stock as well as the new buildings. You can do a lot in new buildings, of course. We have already a European directive now that stipulates zero energy buildings in the medium term. But especially in Europe, that's only a small part of the stock. It's looking a bit better in the developing economies where they're really building up the stock. You can, I think by 2050, you can have about 50% of the stock being built after today. So there, the new build standards can really make a difference. But you do have to think about retrofits, and we've been very ambitious with that. But we've said that you can retrofit to a standard which essentially means you can provide most of your heating needs with, as others have said, heat pumps and solar thermal. That's after doing all of the insulation that's possible. And there are passive-like solutions for cooling as well. And the heat pumps, as others have said before, will contribute to a large increase in electricity. Appliances are in there as well, it's all together. Same picture as before. This is the activity indicator. This is global stock, current versus new. And this is the efficiency indicators. So it's basically electricity in these 2 lines split by residential versus commercial buildings. And these are the heat lines. And this is really assuming really stringent retrofits. Retrofitting basically to zero heat needs, Although you have to remember that the electricity here includes heat pumps for residual heat. So this is why this heat line goes almost to zero. It's because it's being shifted to electricity. Last but not least, in transport, similar picture. No major reduction of travel volume, quite a bit of electrification, but not for all forms of transport. You can't electrify shipping just yet. You can't electrify aviation, and you can't really reasonably electrify sort of long-distance freight, etc. So, and we've even allowed for some of the vehicles in rural areas to remain on at least hybrid forms of transport because of the distances that have to be traveled. So again, the same picture. This is overall activity trends, which we haven't modified, have almost not modified at all. We've put a little bit of modal shift in, but to sort of non-motorized transport for pedestrian transport, etc. But that's such a small share of the overall volume. It's really not making a dent. So most of it, again, is being done with efficiency. And with electrification, there's actually quite a lot of electrification in here, but it doesn't show up as much because it's a much more efficient form of transport. So in the overall picture, it looks really small. But it's a large share of the volume that's being moved to electric transport. So that's the overall picture on the demand side. And then I'm going to go to the supply side, which I think most of you will be interested in. And just to say on the demand side as well, there is really a lot of electrification in there. And always remembering that for the heat and the fuels, they'll always look a little bit larger than the electricity if you were to plot, say, the actual useful energy coming out at the very, very end user. It would look different. So this looks small, but it's actually quite a lot. Right, this question about intermittency and variability. This is what this purple wedge, all of the electricity, looks like on the supply side bar. So we've gone through that purple wedge and gone through all of our supply side electricity options, and we've gone in the order of renewables first, then biomass and others, and matched them, and this is what we come up with. And FYI, if you're interested, so the way that we match them is not just taking one option first, but we look at the split of different renewable power options within a region and just sort of split things proportional from one year to the next. The intermittency question, Yves said at the beginning that just because you call it variable doesn't solve the intermittency issue. That's true. And the reason that people rename things is because it's difficult to communicate. As soon as you call something intermittent, there's a sort of connotation there. And we had the same conundrum in the discussions we were having with the lay public, etc. And so we came up with our own term, which was supply-driven versus demand-driven. But it all means the same thing. Some of them you can steer and some of them you can't. And we put a cap, a variable cap or an increasing cap over time onto the supply-driven sources, so your wind and your solar, etc. And we let it rise, I can show you in the next slide, to about 60% by 2050. Obviously, that assumes a huge investment in grids, both transmission, storage, and demand-side management. But we feel that if you were to invest that money, that's how far you could go. So we started in the early years. We said, well, you could probably do with sort of 20 to 30% before you go into run into trouble, and then you have sort of maybe 10, 15 years of investment. And once that takes off, you could be in a position where you could allow more of that onto the grid. We don't think you can go beyond 60% without installing quite a lot of overcapacities. So the rest, the other 40%, we basically have to do with the demand, what we call demand-driven sources, in which we include not just hydropower and biomass, although that's not a lot, but also geothermal, which can be steered, and concentrated solar power, which with the storage options that are coming onto the market now, of a couple of hours, especially in the evening where you need them, to all intents and purposes can be used as demand-driven sources. That's the power wedge, so you can see how this demand that we had, and we're now filling up with supply options from the bottom. These are all of the supply options that come in from non-biomass renewables. And then I want to spend a little bit of time talking about the biomass wedge. Again, there's a big study behind that, which I'm not sharing today, but come and ask me if you're interested. So the biomass is primarily used for, obviously, transport fuels in the areas where you can't electrify, and in industry fuels where you just need fuels materials. And we've given priority, or put it this way, we've tried to do our best to avoid having to use the biomass in buildings, because we know that a lot of it is needed for transport and industry. So just to talk you through the potential assumptions, so how we estimate the potential for biomass on this side, and then we then run this through a sort of big virtual biomass refinery to get our various outputs out. So the way that we run this is we account for traditional biomass. We phase that out generally because it's something that's generally considered unsustainable, but we do retain a small share of it, maybe a third, that we think you could harvest sustainably. So there's certainly some forest harvesting. If you did that commercially and you use it for lignocellulosic fuel production, that could be used. Except we don't. We use it for combustion. Apologies. Then, in terms of the merit order, the first wedge we use is residues and waste. That's something I haven't heard many people talk about yet in this conference. I think some people said forest residues and wood waste. So that's from existing commercial operations, both primary and secondary residues can be used. But what people haven't talked much about, because it's a small potential, but it can be useful, are oily and fatty residues in municipal waste or industry waste, as well as dry wastes. And then, of course, there are agricultural residues. And we have made sure that we've allowed for competitive uses where you need to leave stuff on the land, etc. So we feel that the potentials we've assumed here are sustainable potentials for these biomass sources. We've also got a wedge which we call complementary fellings. So that means forests which are, we call them disturbed forests. So they're not pristine rainforests or so. They're forests which already have sort of roads running into them not far away, which could be used commercially to both manage the forest and gather additional biomass. So that's that wedge. And only then do we go to what most people think of when they hear biofuels, which is crop-based biofuels. We treat them in 3 different types. Those are oily, sugary, and the woody crops, because they have different conversion routes and different yields. And then we throw in one more technology there, which is algae-based biofuels. They don't come in until after 2030, and they're a bit of an outlier. Generally, the technologies we've assumed are all technologies that are available now, and this one is one that's on the horizon, and we feel it's got high promise. So we've put it in at least a small amount after 2030, and it would make a big difference, because basically we only have biomass to deal with our fuels, whereas for power we have lots of options. And especially in the fuels, the transport fuels are difficult to replace, and oily stock is really useful for these high energy density transport fuels. So that's the overall picture in the end. We've filled up all of our demand with the various supply options. First, renewable power options, then the biomass, and then we fill the rest with the traditional carriers. We don't exclude any carriers. We don't have a sort of pre-exclusion of nuclear or so. We also don't have a pre-exclusion of CCS, but we just find that once you go through this merit order, you just don't need it in the end. Now, I just have to say, so this is a sustainability-driven scenario, right? So our merit order is, sorry, I don't mean merit order in the grid sense. I mean our order of options is sustainability-driven. So it's not a cost-driven scenario in any sense of the word. But we wanted to, of course, know whether it's affordable. Because when you want to answer the question, is it feasible? You can say it's technically feasible, but of course you have to answer the question whether it's affordable. And so what we did, and that's actually the hard part, and that's why most people don't take this approach. They don't take the physical approach of finding out how you change your industrial processes and how you change your buildings, because you then have to go and quantify how much it costs to retrofit a building to a certain standard, or how much it costs to upgrade your grid, and how much it costs to change your industrial options. And there are huge uncertainties in those estimates, but we tried. We wanted to at least know whether it's a crazy idea or whether it's feasible. And our feeling is that it's feasible. So we went through all the sectors. We tried to estimate how much it might cost. And we come up with these figures, which basically say that, and I have to explain here, this is time running along this axis, and then it's our net costs, which is the sum of the capex, so the investment cost, and the opex, which are all additional to baseline, so additional costs. And these are all expressed as % of GDP in that year. This is not showing annualized costs, so it's what you might call a cash flow approach. And I'm not an economist, someone else did this work, but it's a cash flow approach. So we're really trying to show how much you have to spend in which year. So the point is that you've got these massive investment costs at the beginning because you have to retrofit all of your buildings, you have to build some infrastructure, etc. And then as you come to the end of your retrofitting and you start reaping the energy savings, that's when your net costs turn negative. And that's of course pointing out the obvious. If you think about it from a common sense point of view, you have to make the investments now, but at the end of that you have an energy system which is much cheaper to run than what we have now. The difficulty is making those investments, and that's why we showed the cash flow approach, just to see whether it's prohibitively much in any given year. Yeah.
Just the question about the cusp here. I mean, you have change of slope. What happens at that point so that you have?
Yeah. So I also have to explain. We do this in 5-year intervals. So this is not we don't do every year. So something happens between those 2 years where I guess we've just finished doing that last bit of retrofit, and we stop doing that, and then we start saving. I could look into, but I can look into the individual numbers. Sorry, and I should say, so it looks like it's affordable, but of course, as you all know, there are real reasons why this doesn't happen. There's a difficulty in long-term planning if you leave things to the market, because obviously business leaders have responsibilities to their shareholders which don't look at 20-year time horizons. So there are good reasons why people do short-term instead of long-term planning. And then there are, they are large investments, they're not trivial sums, and there's also an issue just around access for money. So even if you had a good idea and you think you can pay back maybe in 5 to 10 years, you still have to find someone to give you the money. Just a quick comparison with other scenarios. This is showing primary energy because most scenarios do report on primary energy, so we transferred our numbers into those units, and you can see that obviously we're far out. It's a very ambitious vision. The green line there is the Greenpeace revolution, which is a similar sort of set, and in purple there you see the World Energy Outlook recent scenarios, which I think the 450 scenario is the one that might have a chance of 2 degrees, and then there's the current and new policy scenarios there. And you can see oceans and mountains as well.
10 minutes.
Yeah, now I'm basically done. Yeah, the obvious question is, well, that would be nice. We're over here and we want to go over there. How do we do that? And that's where all the hard work starts. So obviously there are things to do around incentives and standards for efficiency. There's actually a lot we can do there. A lot that is done in various regions of the world, but we're not doing it across the whole board. A lot of investments required in infrastructure. And all the issues around the power system, we've already talked about that. So that's really the last slide, summary slide on what you have to do. I'll just quickly go through them. The first thing to do really is maximize efficiency to stabilize and reduce your demand. Then electrify as much as you can, because that's where all of your renewable options are. To do that, though, you have to prepare your electricity grid, and we've already missed the ball on that, but I hope we can still catch up and at least do this maybe 5 to 10 years late. You then scale up your renewable power options once you've done that. And once you've done your power, you need to provide options for fuel and heat, which will be primarily bioenergy. There are some interesting other ideas, but I think they'll take longer to develop. And if you did that, you could, I think, have an energy system at the end which would be cheaper to run. But that's quite a large societal effort if you wanted to make it true, so that's the challenge. I think that's it.